Dear students, welcome to my channel. Topic of this video is image transform. This is the second video on this topic, and in this video I am going to discuss Walsh Hadamard transform. Now let us start. The Walsh Hadamard transform is a digital signal processing technique used for data compression, feature extraction and signal analysis. Decomposes a digital signal into set of basis function. These Walsh functions are square waves with values of +1 or -1 over a specific interval. In my previous video, we have already seen this Hadamard-Walsh matrix for orthogonality checking and for unitary transform checking. Now, while checking for orthogonality, we found out that when we use simple this equation, at that time we are not getting the perfectly identity matrix. To get the particular perfect identity matrix, we require to multiply it by this factor. So here I have represented the equation in both form, that is not normalized and normalized. So h of 1, in which only one element is there, and here it is multiplied by 1 by square root of 1. So no need to write down that. H of 2 is 1 1 1 minus 1, and in normalized form we require to multiply. The order of this matrix is 2, so we require to multiply it by 1 by square root of 2. This is h of 4 matrix. For normalization we require to multiply by 1 by square root of 4. Similar h2 h4 we can write down the h8 also. For h8, for normalization we multiply by 1 by square root of 8. Similarly h8 we can generate, the next is h16, then h32, h64 in such a way that now how to generate that we can use the recursive equation to generate this Walsh Hadamard matrix. And during calculation also sometimes we use not normalized form and sometimes we use normalized form. So any form we can use, only there is need to change this particular multiplication factor. Now we will see the recursive generation, that how this Hadamard matrix, Walsh Hadamard matrix of different order gets generated using recursive equation. Formula is h of 2 raised to n is equal to h of 2. This is the Kronecker product. So in my previous video I have already explained how to do or how to apply the Kronecker product on the matrices. H of 2 Kronecker product h of 2 raised to n minus 1. Now we take n is equal to 1, then it becomes h of 2 raised to 1, h of 2 into h of 1 minus 1. So 1 minus 1 is 0, 2 raised to 0 is 1, and h of 1 is only one element. So we are getting h of 2 is equal to h of 2 because this is only one element. So Kronecker product becomes the h of 2 only. For n is equal to 2, we are getting h of 2 square is equal to h of 2. Kronecker product h of 2 raised to 2 minus 1 is 1. So this is nothing but h of 2 cross h of 2, we will get h of 4. For h of 8 we are using the 2 raised to 3, that is n equal to 3, and we get h of 2 Kronecker product h of 4. If we want to apply h of 16, then with the help of h of 2 we can generate this matrix also. So this is nothing but the h of 2 Kronecker product h of 8. In this way we can generate the variety types of Walsh Hadamard matrix of a particular order. Now we will see how to generate h of 4 using the Kronecker product. H of 2 cross h of 2, this is we already seen in the previous slide. Now we require to use the Kronecker product. So for Kronecker product, we are using this one matrix is multiplied to the all elements of this matrix, that is nothing but 1 into this, then this one matrix multiplied by all the elements, then this is 1 into this entire matrix, then this 1 into to entire matrix, and this minus 1 into entire matrix. So 1 1 1 minus 1 we will get this, then 1 1 1 minus 1 we will get this, then 1 1 1 minus 1 we will get this, and when we multiply with minus 1 we are getting this. So by this, using the recursive generation and Kronecker product, we can obtain the Walsh Hadamard matrix of order 4. To generate for h8, we get the equation, that is h of 2 cross h of 4. So here we are using this h of 2 is 1 1 1 minus 1, and this h of 4, this is h of 4. Now we multiply with h of 2 Kronecker product h of 4. So here this one we multiply with this entire 4 by 4, then this one with the entire this 1 and minus 1. So we are getting like this, and here for this 4 by 4, this first block, then the second block and third block, all three blocks are same, that is 1 to 3 because it is multiplied by 1. Only last block the sign will change. So in this way, by using the recursive generation and by using the kronecker product, we can obtain the Walsh Hadamard matrix of any order. Now exercises on one-dimensional signal. To convert one-dimensional signal from time domain or spatial domain to Walsh Hadamard domain, that is nothing but frequency domain. So formula is x of n is equal to h of n into x of n. This small x indicates we are in spatial domain and time domain, and small indicates is nothing but we are in that domain. And for change domain, we always use capital and capital N. X is the input signal in spatial domain, h of n is Walsh Hadamard transformation matrix, and x of n is nothing but the transform signal. Every transform is recursive in nature, so we can obtain our original signal by using this. X of n is equal to 1 by n h of n into x of n. Now here we are using unnormalized transformation matrix. We can use normalized also, only if we use normalized then change in formula, otherwise the entire procedure is same. But for simplicity we are using unnormalized transformation matrix. Now first problem, convert a given signal 1203 into Walsh Hadamard transform domain and again convert back to the original signal, or prove that Walsh Hadamard transform is a reversible in nature. So when we get x of n into Walsh Hadamard and from Walsh Hadamard to again this same signal, then the transform is reversible in nature. Formula is x of n is equal to h of n into x of n. H of n, now this signal having the length of 4, so we are going to use h of 4. H of 4 multiplied by this signal, we get 6 minus 4 2. Now I am not explaining the matrix operation because you are already aware how to do the matrix multiplication. Now important observation we have to do that. For example, in the first step we are doing multiplication of 1. There is no actually as such need that we should multiply with 1. And even in hardware, when we are using -1, then we can use the negate circuit or negation and we can do with -1. So first see, when we are generating 6, actually we are adding 1 plus 2 plus 0 plus 3. So 1 plus 2 plus 0 plus 3. So we are using addition operation for 3 times, 1, 2 and 3, and this step is repeated for 4 times. So we are totally use that 4 into 3, that is 12 operations, that is 12 addition operation. So total additions for this signal is n into n minus 1, which is nothing but equal to 4 into 4 minus 1, 12. Now again we require to convert the signal from Walsh Hadamard domain to the time domain or spatial domain. So we are using 1 by n as a factor. So is matrix is of order 4, so 1 by 4, this is h of n and this is our x of n. If we do this operation, we are getting again original signal back. So it proves that Walsh Hadamard transform is a reversible in nature. So this is another example, 5731. We will do the same operation. Number of additions are n into n minus 1, which is equal to 12. And for reverse, we are using only the constant, that is 1 by n, h of n into x of n. So when we 1 by 4, this is h of n and x of n, we again get back the original signal. So these problems are for one dimension signal. Now we can go for the two-dimensional signal. For two-dimensional signal, we will again take the example on one-dimensional signal, in which the signal length is 2, that is only 2 samples are there, and we convert into the Walsh Hadamard transform. When the sample is only 2, then we can go for this h of 2. So formula is h of n into x of n, we will get this. So here total number of operations are n into n minus 1, that is equal to 2, because see here we can use 13 plus 15, so one addition operation is there, and then 13 minus 15, that is one addition operation is there, so 2 operations are used. When we want to make reverse back, only we require to remember that this 1 by n should be used, so 1 by 2, and we will get the signal original back. So here only in input problem, this is 13 not 12, so this is 13. This is another problem with signal 711. Similar way, this is Hadamard matrix, input signal, do the multiplication, we will get this value. After that, to get back our original signal 1 by n, again h of n into capital X of n, again we will get back the original signal. Now for n equal to 8, the total addition operations, that is total addition operations are n into n minus 1, which is equal to 8 into 756. As size of n increases, the number of operations are increasing exponentially. To overcome this, we are not using simply multiplication of transform matrix to input signal, but we use the fast Hadamard transform. So in my next videos, I will explain how to perform the fast Hadamard transform using the butterfly diagram. Exercises on two-dimensional signal. Now when we move from one-dimensional signal to the when we convert two-dimensional signal from time domain to Walsh Hadamard, we require to multiply the Walsh Hadamard, that is transformation matrix, by twice. So h of n, this is our signal which is in two dimension, again h of n. And for reverse, instead of 1 by n, now we are using 1 by n square, because we are using h of n twice, h of n, x of n and h of n. So when we use this, then we will get again the original 2 by 2 matrix. Now this is signal, that is x of n is given, then this h of n, that is h of 4 into our signal into again h of 4. So first we multiply these two matrices, we will get this result. After that, this result and the next matrix, we will get the final result. So this is nothing but the final Walsh Hadamard transform signal. To get back original, we require to do the same operation, only this will be replaced here, and we require to use 1 by n square, that is nothing but 1 by 16. So only first we will do this multiplication, answer is this, then this, and remaining this, we will get again original signal back. Now next, one more example. So this is input signal, again it is two dimensional having the order of 4. So we are using h of 4, we are doing this multiplication. First to this matrix multiplication and their resultant into this, and we will get this signal. This is same as our previous example. Now to get back the original matrix, again we are doing 1 by n square, this operation, this is nothing but our x of n, multiply these two first, we get this intermediate result, and after that we multiply this and we get the final result. So input signal we get as it is from the transform domain. Now this example is given in which sizes of the matrix is 2 by 2. So we are using h of 2. So we have to check whether to go for which order of h matrix based on our input signal. So formula is same, that is nothing but h of n into x of n into h of n. So we multiply this, we will get this, and in the reverse operation we are using 1 by n square. So n is 2, so 1 by 4, and when we multiply these two, we will get this result, and this multiplication and into 1 by 4, we will get again original signal back. Convert given 1D or 2D signal to Walsh Hadamard transform. If 1D signal contains 3 values, we have to append one more 0 to make the size of 4, to use the h of 4, because this is always order of 2. Similarly, if 2D signal similarly for 2D signal, we append zeros to make the data perfect for multiplication. So we require to put our data either in the order of h of 2, h of 4, h of 8 and dash 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 in the power of 2. So this is all about Walsh Hadamard transform, that is how we are taking the signal and converting to the Walsh Hadamard domain and again back to the original domain. In the next video, I am going to explain the similar for Walsh transform and for Fourier and DCT. Thank you.